Welcome to the Insightful Professor. Today we continue our examination of malware and cyber attacks. In this video we'll be talking about computer worms. We'll provide a little background on the history of worms and explain how they operate, giving examples of some of the more notable incidents that have occurred. So what exactly is a worm? Well, a simple definition is a worm is a program that actively seeks out more machines to infect, and each infected machine serves as an automated launching pad for attacks on other machines. Well, from this definition, we have to have some initial point of origin. The machine on which this software resides that's seeking out to attack other machines has to become infected. We'll talk about how this might occur as we investigate worms in some detail. But first, let's go back a few years and see where the term worm originated. The concept of a computer worm was introduced in a science fiction novel in 1975 called The Shockwave Rider. The hero uses computer hacking skills to escape pursuit. The book coined the term worm to describe a program that propagates itself through a computer. In this book, the author developed the notion of an omnipotent tapeworm program running loose through a network of computers. The basic model has a program or a computation that can move from machine to machine, harnessing resources as needed and replicating itself when necessary. The first known worm implementation was done in Xerox Palo Alto Labs in the early 1980s. It was non-malicious. It was searching for idle machines to use to run a computationally intensive task. The installation had about 100 independent machines connected to a network, and they were trying to more efficiently utilize these resources. So what does a worm do? Well, a worm exploits software vulnerabilities in a client or server program. It can use network connections to spread from system to system. It can also spread through shared media, such as a USB drive, a CD, or something of that sort. Email worms spread in macro or script code included in attachments and instant messenger file transfers. We talked about this means of propagation when we were discussing viruses. So this is going to be quite similar. Upon activation, the worm may replicate and propagate again. It usually carries with it some payload. To replicate itself, a worm uses some means to access remote systems, and these include electronic mail or instant messenger. Worm email code is run when the email or attachment is received or viewed. Another form of replication is file sharing. After infection, the worm executes when the drive is connected to another system using the auto-run mechanism by exploiting some software vulnerability, or when a user opens the infected file on the target system. A remote execution capability. Here the worm executes either by using an explicit remote execution facility or by exploiting a program flaw in a network service to subvert its operations. We'll discuss this in some detail when we examine the Morris worm. Remote file access or transfer capability. Here the worm uses remote file access or transfer service to copy itself from one system to another. And with the remote login capability, the worm logs onto a remote system as a user and then uses commands to copy itself from one system to another. The end result of this replication is that the new copy of the worm program is then run on a remote system, where, in addition to any payload functions that it performs on that system, it continues to propagate. A worm typically uses the same phases that we discussed for a computer virus. There's a dormant phase, a propagation phase, a triggering phase, and an execution phase. The propagation phase generally performs these functions. It searches for appropriate access mechanisms to other systems to infect in a variety of ways by examining host tables, address books, and so forth, scanning possible target host addresses, searching for suitable removable media devices to use. And it uses the access mechanisms that it discovers to transfer a copy of itself to the remote system, and then cause the copy to be run. The worm may also attempt to determine whether a computer system has previously been infected before copying itself to the system. In a multi-programming environment, it can also disguise its presence by naming itself as a system process or using some other name that may not be noticed by a system operator. More recent worms can even inject their code into existing processes on the system and run using additional threads in that process to further disguise their presence. The first function in the propagation phase for a network worm is for it to search for other systems to affect. This process is referred to as scanning or fingerprinting. To exploit software vulnerabilities in accessible network services, a worm must identify potential systems running the vulnerable software and then proceed to infect them. Once installed on infected machines, a worm repeats the scanning process, creating a distributed network of infected machines. So what techniques can be used for scanning? We'll discuss random, hit list, topological, and local subnet to give you an idea of how the scanning or fingerprinting process would work. The first network address scanning strategy we discuss is random. Each compromised host probes random addresses in the IP address space. This technique produces a high volume of internet traffic, resulting in a disruption to normal network activity before the actual attack is launched. The second strategy is referred to as a hit list. Here, the attacker first compiles a long list of potential vulnerable machines. This would be a list of IP addresses. This can be a slow process done over a long period to avoid detection that an attack is underway. Once the list has been compiled, the attacker begins infecting machines on the list. Each infected machine is provided with a portion of the list to scan. This strategy results in a short scanning period, which may make it difficult to detect that infection is taking place. Another strategy is referred to as topological. This method uses information contained on an infected machine to find more hosts to scan. This information might be taken from a web server log or email address book or some kind of configuration file. And finally, we mention local subnet. If a host can be infected behind a firewall, that host then looks for targets in its own local network. The host uses the subnet address structure to find other hosts that would otherwise be protected by the firewall. A well-designed worm can spread rapidly and infect massive numbers of hosts. Both computer viruses and worms exhibit similar self-replication and propagation behavior to biological viruses. The propagation proceeds through three phases. There's an initial phase where the number of hosts increases exponentially. Consider a simplified case in which a worm is launched from a single host and infects two nearby hosts. Each of these hosts infects two more hosts, and so on. This results in exponential growth. Next, after some period of time, infecting hosts waste some time attacking already infected hosts, which reduces the rate of infection. During this middle phase, growth is approximately linear, but the rate of infection is rapid. Finally, when most vulnerable computers have been infected, the attack enters a slow finish phase as the worm seeks out those remaining hosts that are difficult to identify. The objective in countering a worm is to catch the worm in its slow start phase at a time when few hosts have been infected. We interrupt our regularly scheduled lecture to bring you an announcement on Buffer-Overflow Attack. Another method of attacking a system is called a buffer overflow or buffer overrun attack. We recognize that programs operate on data, and when a program executes, it will be passed data in some form. The data must be stored in memory in order for the program to operate on it. It's stored in what we refer to as a buffer. A buffer overflow occurs when someone tries to put more data in a buffer than that buffer was designed to hold. The possible consequences of this act would be the program crashes. If the memory that's overwritten contains executable instructions that are overwritten with garbage, the program terminates with an error. Another possible consequence: data are corrupted. If the memory that is overwritten contains data in other variables or work areas, the data are now likely invalid. It's quite likely that when the overwritten data is used in subsequent processing, the program will again terminate with an error. Consider that one of the variables was a number used in computation. Due to the buffer overflow, its content no longer reflects a valid number. The next attempt to access and use this variable in an arithmetic operation will result in an error. The third consequence: the program execution is hijacked. By sending carefully crafted input to an application, an attacker can cause the application to execute arbitrary code, possibly taking over the machine. Let's consider how this might work. Suppose a program has a buffer size of 1,000 bytes. Beyond this storage, beyond this buffer, could be storage for other variables or executable instructions. If attention is not given to the size of the data passed to the program and placed in the buffer, the program will accept a larger amount, say 2,000 bytes. What happens to that extra 1,000 bytes that can't fit in the buffer? A well-written application will deal with such an attempt by truncating the data or by rejecting the oversized data altogether. Programming languages like C and C++ are prone to buffer overflow attacks, as they have no built-in protection against accessing or overwriting data in any part of their memory, and as actors can perform direct memory manipulation with common programming constructs. Modern programming languages like C#, Java, and Perl reduce the chances of coding errors, creating buffer overflow vulnerabilities. But buffer overflows can exist in any programming environment where direct memory manipulation is allowed, whether through flaws in the program compiler, runtime libraries, or features of the language itself. Techniques to exploit buffer overflow vulnerabilities vary based on the operating system and programming language, but the goal is always to manipulate a computer's memory to subvert or control program execution. Buffer overflows are categorized according to the location of the buffer in the process memory. The two main types being stack-based overflow and heap-based overflow. This concludes our special announcement. We now return you to your regularly scheduled lecture. We discussed buffer overflow prior to jumping into our discussion of Morris worm. The reason being, it is an exploit used in several historical attacks, including the Morris worm. The Morris worm was the first really significant worm that effectively shut down the internet for several days in 1988. It's named after its author, Robert Morris, who was a graduate student at the time. It was designed to spread on Unix systems. Not all Unix systems. There was a certain version of Unix that was targeted. In this worm, there was code that attempted to crack a local password file to use login password information to log into other systems. Now, this was a vulnerability in the Unix systems that the password file was publicly accessible. Furthermore, the worm exploited a bug in a program called Finger. And we'll talk about that in just a moment. That's where the buffer overflow came into play. It also exploited a trap door available through a program called SendMail. When the program operates in debug mode, we could do additional things that we normally couldn't do. So these are the 3 points that were critical to how the Morris worm operated. We'll take a look at these in just a moment. Now, successful attacks achieved communication with the operating system command interpreter. It sent to the interpreter a bootstrap program to copy the worm. Now let's get into some details about what happened here. At the time the worm attack took place, it was possible to send a message to the SendMail program running on a remote machine with the name of an executable as the recipient of the message. If the SendMail program was running in debug mode, it would then try to execute the named file, the code for the execution being the content of the message. The code that was executed stripped off the headers of the email and used the rest to create a small bootstrap program in the C programming language that pulled in the rest of the worm code. There was a bug in the Finger daemon of that error. The Finger program suffered from the buffer overflow problem that we discussed. If an executing program allocates memory for a buffer on the stack, but does not carry out a range check to make sure that the data stays within the stack, it's not larger than the stack, what will happen is you can encounter this situation where the data overwrites the program instructions on the stack. A malicious program can exploit this feature to create fake stack frames and cause the rest of the program execution to be not as it was originally intended. The worm used the remote shell program, RSH, to enter other machines using passwords. It used various strategies to guess passwords. This is akin to what is now commonly referred to as a dictionary attack. Let's examine a few more recent worm attacks to get an idea of how malware has evolved. The Melissa email worm appeared in 1998 as the first of a new generation of malware that included aspects of virus, worm, and Trojan in one package. Melissa used a Microsoft Word macro embedded in an attachment. If the recipient opens the email statement, the macro is activated. It then sends itself to everyone on the mailing list in the user's email package, propagating as a worm. It does local damage on the user's system, including disabling some security tools and copying itself into other documents, propagating as a virus. If a trigger time was seen, it displayed a Simpson quote as its payload. A more powerful version of this email virus appeared in 1999. It could be activated by opening an email that contains the virus rather than an attachment. The virus uses the Visual Basic scripting language supported by the email package. SQL Slammer is a worm that hit networks in 2003. The Slammer worm affected only machines running Microsoft SQL Server 2000. This system supports a directory service that allows a client to send a UDP request to quickly find a database. At the time the worm hit, this feature of the Microsoft software suffered from the buffer-overflow problem. Slammer just sent one UDP packet to a recipient. The SQL specs say that the first byte of this UDP request should be a hexadecimal 04, and the remaining, at most, 16 bytes should name the online database being sought. The specs further say that this string must terminate with a null character. In the UDP packet sent by the Slammer worm to a remote machine, the first byte, hexadecimal 04, was followed by a long string of bytes and did not terminate in the null character. In fact, the hexadecimal 04 byte was followed by a long string of hexadecimal 01 bytes, so the information written into the stack would exceed the 128 bytes of memory reserved for the SQL Server request. It is the overwrite portion of the Slammer that executed its network hopping code. It created an IP address randomly for the UDP request to be sent to another machine. This code was placed in a loop so that the infected machine would constantly send out UDP requests to remote machines selected at random. MyDoom. MyDoom is a mass mailing email worm that appeared in 2004. It followed the growing trend of installing a backdoor in infected computers, thereby enabling hackers to gain remote access to data such as passwords and credit card numbers. MyDoom replicated up to 1,000 times per minute and reportedly flooded the internet with 100 million infected messages in 36 hours. The Configure worm. By all accounts, this is the most notorious worm that has been unleashed on the internet in recent times. As reported widely in the media, the worm was supposed to cause a major breakdown of the internet on April 1st, 2009, but nothing happened. The current best speculation is that the worm was let loose by one or more organizations to test its power to propagate using what is now known as MS-0867 vulnerability of the Windows machines of that era. The speculation has been reinforced by the fact that another worm, Stuxnet, which was let loose in 2010 shortly after Conficker started making the rounds, shared several similarities with Conficker with regard to how it broke into other machines. As widely reported by the media at the beginning of this decade, Stuxnet was used successfully to sabotage the nuclear program of a country. Stuxnet is a classic example of weaponized malware. It first spread via infected USB drives. However, once it was on an infected machine, it would spread over the entire network and even over the internet. The Stuxnet virus then searched for a connection to a specific type of programmable logic controller. If that particular PLC was discovered, Stuxnet would load its own copy of a specific DLL for that PLC in order to monitor the PLC and then alter its functionality. Stuxnet was designed to target centrifuge controllers involved in Iran's uranium enrichment, but the virus spread beyond its intended target and thus became publicly known. While many users reported no significant damage outside the Iranian reactors, it was detected on numerous machines. Stuxnet employed a classic virus design. There were three modules: a worm that executes routines related to the attack, a link file that executes the propagated copies of the worm, and a rootkit responsible for hiding files and processes, all with the goal of making it more difficult to detect the presence of Stuxnet. There was a ransomware attack in May 2017 that spread extremely fast over a period of hours to days, infecting hundreds of thousands of systems belonging to both public and private organizations in more than 150 countries. It spread as a worm, aggressively scanning both local and random remote networks, attempting to exploit a vulnerability in the SMB file sharing service on unpatched Windows systems. This rapid spread was only slowed by the accidental activation of a kill switch domain by a UK security researcher. Once installed on infected systems, it also encrypted files, demanding a ransom payment to recover them. Take a look at the state-of-the-art for worm technology. Multi-platform. Newer worms are not limited to Windows machines, but can attack a variety of platforms. Multi-exploit. New worms penetrate systems in a variety of ways. Ultra-fast spreading. They exploit various techniques to optimize rate of spread. Polymorphic. Each copy of the worm has new code generated on the fly. Metamorphic. In addition to changing their appearance, metamorphic worms have a repertoire of behavior patterns that are unleashed at different stages of propagation. Transport vehicles. Because worms can rapidly compromise a large number of systems, they are ideal for spreading a wide variety of malicious payloads. Zero-day exploit. To achieve maximum surprise and distribution, a worm should exploit an unknown vulnerability that is only discovered by the general network community when the worm is launched. In 2015, 54 zero-day exploits were discovered and exploited, significantly more than in previous years. Many of these were in common computer and mobile software. Some, though, were in common libraries and development packages, and some in industrial control systems. This indicates the range of systems being targeted. NIST SP 828 defines mobile code as programs that can be shipped unchanged to a heterogeneous collection of platforms and executed with identical semantics. These are transmitted from a remote system to a local system and then executed on the local system. It often acts as a mechanism for a virus, worm, or Trojan horse, and it takes advantage of vulnerabilities to perform its own exploits. Popular vehicles include Java applets, ActiveX, JavaScript, and VBScript. The most common ways of using mobile code for malicious operations on local systems are cross-site scripting, interactive and dynamic websites, email attachments, and downloads from untrusted sites or of untrusted software. Mobile phone worms were first discovered in 2004. Then additional worms were discovered in 2005. These communicate through Bluetooth wireless connections, or MMS. The target is the smartphone. Such worms can completely disable the phone, delete data on the phone, or force the device to send costly messages. ComWarrior, discovered in 2005, replicates by means of Bluetooth to other phones, sends itself as an MMS file to contacts, and as an auto-reply to incoming text messages. These early mobile worms targeted mobile phones using the Symbian operating system. More recent malware targets Android and iPhone systems. Mobile phone malware can completely disable the phone, delete data on the phone, or force the device to send costly messages to premium-priced numbers. From these examples, we see that mobile phone worms are possible, but the vast majority of mobile phone malware observed use Trojan apps to install themselves. Let's conclude our examination of worms. In this video, we explained the concept of a worm, discussed characteristics of worms, explained how worms replicate, introduced the idea of a buffer-overflow attack, and discussed some of the most notable worms. Our comments on worms make them sound much like viruses. So what's the difference? Well, one obvious difference: a virus attaches itself to some executable code. It executes when this host program runs. A worm is a program that can run independently. In our next video, we will continue our investigation of malware and cyber attacks by investigating various types of cyber attacks. We'll consider the topic of ransomware in more detail.